So, basically, Sahil, what we are having in these sessions is we discuss the previous year assignment questions. So that helps you to understand the concepts in a problem solving approach, and then you can also attempt the current assignments. So we focus mainly on solving the questions from previous years, that is the 24 edition. Then 23 edition questions are also there. There might be some extra questions which are not from the assignments, but then they are also related. So these will be MCQ based questions. So what we usually do is that uh, we want like I'll read out the question for you, and then I would like you to answer the question right in the chat box, or even you can unmute and then try to answer. And yeah, this session is for 2 hours. Every Tuesday we have these sessions, and in like today is the week five session, so we will cover the week five content, which is I think emotion in speech. So today we will be covering that only. Let me share my screen. I think some problem is there. Also, Sahil, you did not attend the previous session, so we record these sessions and all the presentations like that I use, and all the sessions are available on YouTube. So the session recordings, video meet recordings are available on the YouTube, and the presentations. I think you might have been shared with you a link, Google Drive link. So I upload these slides to that folder so you can easily access.
Ma'am, are you talking about the previous year assignment questions?
No, like the sessions that we had, this is live session number five. So for the current iteration, we have had week one to week four sessions. Every Tuesday we are having these sessions. So everything that is being, discussed, or everything like these slides that I'm using, this will also provide you some idea. Uh, so you can just refer to these slides, and I mean, since you haven't attended the sessions, so these YouTube channel link will also be shared with you. You can check out your mail, or I don't know where they share it, but then I have to upload the videos, recorded sessions on YouTube. So in case you want to revisit those, they are available on YouTube.
Ma'am, could you send me the link? Actually, I have not received like the link or the Google Drive that you're
Okay,
talking
okay,
about.
sure, sure, sure.
Like maybe on the Meet chat would be great.
Yeah, yeah, that's what I'm going to do. Actually, the sessions are on my personal channel, but the NPTEL team, I think they share this with you.
Um,
So, but I'll still share.
Also, ma'am, is there a PDF for the like previous year assignments that you're talking about so we can practice them?
I think previous year assignments are not as such available, but you need,
Ma'am, like, would you have like a doc or maybe a PDF so that we
yeah,
could
but
practice from there?
so I don't have the exact like from the PD. I have included the questions in this presentation, so you can refer this to cover the previous year questions. But otherwise, I don't have a like proper PDF or something. I also have to refer
Oh,
to some credentials which I cannot share, so that's why.
Oh, all right. No worries. No
Yeah.
worries.
So let me just write down in the chat box, and then we can start the today's session. So you can find out in the recent videos, okay? So I hope you're covering the syllabus that is being discussed in the week's content. So anyways, I will start from like scratch only. Like I assume that you don't have any knowledge about effective computing, whatever
Yeah,
being
ma'am.
discussed in the, yeah.
I'm actually starting from scratch actually,
So it's
because I
fine.
had my college exams, so I was planning on like doing the course from today. So
Okay, no issues at all.
yeah.
I think you will be able to understand the overall concept. So if you have any doubt, please feel free to unmute and then we can have a discussion.
All right, sure, ma'am.
Okay. So the first question is the week's content is basically based on emotions in voice. And I forgot to introduce myself. So my name is Akanksha, and I am a PhD student at IIT Roper. So I am the PMRF TA for this course, and hence I'm taking these sessions. Okay, let's discuss the questions. So emotions in voice. We in the previous editions of these sessions, we have also discussed various approaches or various approaches which use the facial expressions as a cue to uh, detect the emotion being in the picture. So basically, whatever emotion is being displayed by a person, whether in the form of speech or expressions, so affective computing essentially deals to detect the emotions being displayed. So today we are going to discuss about the speech modality, which is the voice. So number one question is what is one of the primary challenges in voice-based affect analysis across different languages? So is it the limited availability of recording devices, difficulty in understanding speech patterns, cross dataset performance variations, or lack of computational resources? So I typically wait for around 10 to 20 seconds so that you can write the answer in the chat box and then I go on to the discussion part. So I'll wait for you. Two, difficulty in understanding speech patterns. Okay, so what are the main challenge in effective system is it is the cross data set performance. Oh, why and why other options are not the correct answer, we will also discuss that. So first is since you know the linguistic differences can be there. What is like every language is different. Every language has some unique phonetic prosodic. You know these terms phonetic prosodic. Prosody is basically the way of the style of speaking. I have a certain style of speaking. You have a certain tone in your voice in which you typically talk like that. So every person has their own style and every person has their own speech characteristics. So these characteristics are typically they vary from every language to language. In Hindi, I might have a different accent, I might have different pronunciations, phonemes, so different syntax can be there. So the intonation also varies. In English, we may use intonation for emphasis, while Mandarin relies on tonal variations. It's more like a tonal variation in the word level, so it changes the whole word's meaning. So this is different in English and Mandarin, let's say. Then second is emotion expression variability. The way that emotion is being expressed in one language might be very different from what is being uh, displayed in another language. Let's say Western cultures are more like open and it's very okay to exhibit exaggerated emotional expressions. However, in Asian society, we tend to stay more like on the calmer side. We don't express emotions that they're not that loud. So the third can be recording conditions and dataset bias. So different datasets can be recorded in different sources. They come from different sources. The recording conditions, let's say the microphone used in some datasets, there might be more clarity, but while in other it might not be that clear. And the speaking environment, there might be a silent room, or in these maybe some crowdy surroundings. So it also depends. It also varies in terms of these factors. Then comes the speakers diversity. Speakers can also vary. Let's say a data set is only focusing on only young people, but maybe old people or children, they are just not they're not having any kind of data or contribution in the data set. So the data set is only focusing on young people. However, we might also, the systems should be very robust. So systems should be able to understand what is being conveyed in um, be it any kind of person, any gender, any age, and so on. So why other options are not correct is that limited availability of recording devices is not some, it's not a major problem. Anyways, whatever comes in the picture, whatever is a more like a monetary issue or resources issue, they are resolvable up to certain extent. But what issues we are talking about, they're more like logical and so that the issues impact the performance of the systems, that they are unbiased or biased, or they are how accurate the systems are. So the first recording devices can be like widely used. We can even use a slightly lesser quality microphone, but anyways we can get the recording devices. Then difficulty in understanding speech patterns. Nowadays, what you are mentioning, that nowadays deep learning methods are there. We don't even have to explicitly take out the features from the sound. So voice patterns, it's not a headache to extract the features. So deep learning algorithms take care of the feature extraction part. So this is not a difficulty. And the third point is lack of computational resources, which talks about the high computational resources such as GPU or TPU. uh, we have many alternatives to that. We can manage with maybe cloud based resources, like maybe collab you can buy, or subscription, whatever. So you can resolve these issues. But if the like what is the major challenge is, if you are using different data sets and maybe training on just one data set, and it might not generalize well to the other data set. So the correct answer would be cross dataset performance variations. This is a very big challenge. So let me
All
just,
right, ma'am. Makes
hmm,
sense.
yeah. Okay. Second is, what is MFCC and what does it stand for in context of audio signal processing? Now, have you heard about MFCC ever?
No, ma'am.
Okay. So in I also work in speech processing. So MFCC is a very widely used features. Do you understand deep learning a bit?
Yes, ma'am, to some extent.
So yeah, so you know the basic terms like features, models, whatever is
Yes,
happening, the
ma'am. Yes,
pipeline.
ma'am.
Okay, great. So MFCC is a audio-based feature. Okay, so we extract these features from. So there is a library in Python called librosa, which is for the speech processing, and we can easily extract these features. So now we will discuss what exactly MFCC is. Although this is very, I would say, complicated to understand. So, and due to time limitations, I'll just give an overview. So what MFCC means is that this particular figure that you're seeing is called a Mel spectrogram. So and the MFCC coefficients are represented somewhat like this graph. So some values might be, you might be able to spot some data here. And what exactly this means is, this is called Mel frequency cepstral coefficients. Uh, it is related to the frequency, the prosody component of the audio. So in whenever we are working with speech data, we need to analyze the speech patterns. We need to extract some features from the speech. Now, um, MFCC is a fundamental feature extraction technique in audio signal processing, especially in speech and affective computing. And what it provides is, it provides us information about short-term power spectrum of an audio. So basically, um, it converts into a set of coefficients. So there might be around 70 or some a number of coefficients that can describe some features. And they are more robust to noise and variations in the recording conditions. And it is considered as a very good feature. And it is used in many tasks. So what exactly the term mel means? This is an important difference. So I wanted to discuss this. What happens is that let's say I talk about frequencies. Humans, we perceive some frequencies. So every sound has a frequency, right? Now what happens is the human ear that we don't perceive the sound on a linear scale. What linear scale means, like let's say there is a frequency at 100 hertz. Now 100 hertz frequency we are hearing. What will happen is if I increase by 100 hertz, now it becomes 200 hertz. So high frequency means the sharper voice is there. Okay, so this becomes more sharp. And if you listen to this frequency, now you can tell the difference between 100 and 200 very well. That 100 is a bit more heavier side, whereas 200 is more on the shriller or sharper side. Now, if the range is very, very high, let's say 8000 hertz, and then I also add 100 hertz to this, it becomes 8100 hertz, right? But if you listen to this and if you listen to this, it will sound very similar to you. You won't be able to tell the difference between the two. Although the difference here also it's 100 hertz and here also it's 100 hertz. So ideally what should be the case that suppose this is the increase in hertz. Let's say I'm increasing the frequency, and this should be like how we perceive, how we hear. So it should be linear. Like if I'm here and then I increase 100, then we should also we should also observe a difference of 100 hertz. But what happens is this is called the linear scale. But then we have a male scale. We do something like this because if even if we the increase is of 100, suppose 100 hertz, the increase here would not be of that much amount. So this is male scale, male representation. So ideally we should design some features which can capture this kind of information. So this is why we need the Bell scale, where which spaces lower frequency more finely and compresses higher frequency because the difference is less. So this is male frequency septal coefficients. I won't go into much detail because it is very tricky to understand because we don't know about the other features, right? So I won't go into the details. But if you, this is a very important feature. Whenever you are starting out with the sound processing or voice processing, you can definitely check this MFCC out. Next question is
All right, ma'am.
what is a spectrogram? Spectrogram is have you heard? So okay, I will go on with the discussion. Okay, if you have any doubts, then you can just stop me and ask the question. So, what is a
Sure.
spectrogram is? Spectrogram is a visual representation. What happens is, even anything that we are representing visually in the form of a graph or a picture, we are able to understand it better somehow, right? So, if I am just telling you something, you won't be able to understand. But if I draw the diagram, it helps us to understand better. Similarly, if we are talking about voices or sound, we have a visual representation which can just summarize the whole information about the frequencies, time, and amplitude. So, spectrogram is a three-dimensional plot. Now, you might say that this is a 2D plot only, but this axis is called the time axis. This is the time that, let's say I have a 5-second audio, so maybe, okay, 4.5. So I have a 4.5 second audio. So this is capturing the whole timestamps. And then we have some frequency hertz range. So let's say this is 8K hertz and this is 512 kilohertz, and then you're representing each point here. It is like at zero point 0.5 second, it contains these all frequencies. So frequencies in our sound or speech particularly, the sound that we hear here it does not consist of only a single frequency. It's a mixture of frequencies. So at every timestamp we might have a combination of frequencies. So I can say that at let's say zero point 0.5 seconds in the audio, I might have let's say 512 hertz, 516 hertz, 1024 hertz, and 4096 hertz. These frequencies are present, let's say for example, and the magnitude is how much this frequency is present. Let's say this is 1, this is 2 times, this is 4, 5 times, and this is 4 times. So these are just the imaginary numbers to make you understand. This is not the actual number. So how we are going to represent it is we will draw a graph at zero point 0.5. I will see wherever 512 I will say 5 for 5 and 2 the value is 1. So this 1, 2, 5 and 4 this is represented by the color. You can see there are multiple like colors here. So the darker the color that means lower the number. You can see here 0 decibels. So that means the amplitude is very low. But the more brighter the brighter the color is, you can see the amount of that frequency is high in that audio at particular. So let's say if we talk about this particular timestamp, so this says that at 1.5 seconds in the audio, the amount of 1024 hertz frequency is given by this yellow color. So it might be in the range somewhere here. So you can see that three pieces of information we are representing in a single diagram. This is called a spectrogram, and this is a very, very important feature that is used in any kind of speech related tasks. So let's read out what it means. We just
Ma'am, so there are multiple output sources for frequencies at the same time.
multiple output sources. So no, actually, whatever we hear is a combination. So many frequencies overlap, and then we hear the combined version. Even the sound production works like that. It's not a single frequency, never. Uh, maybe if you are familiar, like if you hear a piano and if you play a C chord, so C chord also combines like three different notes. So notes are the most like purest form of, you can say, C sharp or C minor, whatever the chord might be. So it is also either a combination of different notes. And if you even play a single note, that is also not a single frequency. It also consists of multiple frequency, and multiple frequencies are such that there is a base frequency and then there are multiples of these frequency. Let's say there is a base frequency of 10 hertz. Then the 20 hertz will be also there. Into 3, 30 hertz will be there. Then into 4, 40 hertz will be there. So combined all, the base frequency will be 10 hertz, but then it also contains a little bit of 20 hertz, 30 hertz, 40 hertz. This is called harmonics. So that is a very complicated task. So every sound that you produce, it is a composite sound. It's not a pure sound. So anyways, we are dealing with the combination of these frequencies.
Got
So
it, ma'am.
hmm. So it is essentially a three-dimensional plot where the x-axis represents the time in seconds or milliseconds. Then the y-axis is there and it represents the frequency. Then the color or the intensity, it represents the loudness, how loud the frequency is or energy of the frequencies. Now, how do we generate this? What we do is, let's say I have audio. I have a audio. Audio can be represented as a waveform like this. Let's say something like this. Now, this is my audio track, okay? And what I do is I break down into small windows. Like I process one window at a time. It usually the windows are overlapping. Okay. So and for this window, like this is one, two, three, four, five, six, depending on the length of duration of the audio. I will take window number one and then apply some fast Fourier transform. Okay, I have mentioned this. We apply the Fourier transform. Then it converts into some, like for window 1, it converts into some coefficient, some numbers. Okay. Let's not go into the detail here, but it converts into numbers. Let's say some values, some values, some values, and then we like plot it in the form of a spectrogram. Okay, so this is what is happening. And why spectrograms are very important? Let's say now we are talking about speech, but let's also take an example of other sounds. Let's say there are multiple sounds such as click or bell ringing, or how do we make the computers understand uh, that this is a bell or this is
Ma'am,
a
your
click?
screen is frozen. Like, I'm not able to see the
Are
like your
you?
screen move.
Is it now visible?
It's stuck at the zoomed picture of spectrogram only.
Oh, let me check.
Even before it was lagging quite a bit.
My internet might be a problem. Is it now better? Can you see the?
No, ma'am. I can see your camera, I think.
Okay. So I'll just leave and I think stop sharing and then share my screen again. Is it visible now, Sahil?
Not yet. Uh,
So
yeah, now it is.
now
Now
it
it
is?
is.
Okay.
I think it's just coming with a bit of delay.
Okay. So did you like were you able to catch this
Ma'am, I
part?
didn't see this diagram at the top. I never saw it.
Okay, okay, okay.
Uh,
So I'll explain it just once more briefly. So this is a audio. This is how we represent an audio signal. Okay. This is the like waveform that you usually see. And what we do is we can break down the audio into a few windows, into smaller segments, you can say, right? Then for each segment, we can process it individually. What we process is that for each window, we apply Fourier transform. Fourier transform, let's not go there, but we apply something called Fourier transform, and that's when Fourier transform, what it does is it converts from the time information to frequency information. Like if you give a segment of audio, it will tell you what frequencies are present in that particular audio. So we get the count and we get the values of the frequencies present, and then we can plot it in the form of a spectrogram. Like that, we generate a spectrogram. Okay, and what I was telling you is that spectrograms usually can be represented as like different forms are there. Like the first one you can say green color or the this is magenta, purplish, but they are literally the same, there's just the color scheme is different. So essentially a spectrogram tells us the intensity. So the brighter the color is, the more energy that the frequency carries. It doesn't matter whether it's green or orange or purple, so just the intensity matters. And what I was telling you, these are the waveforms, like this is the waveform. Are you able to see the screen now?
Ma'am, at the spectrogram, yes. Okay, yeah, now I can see.
Yeah, raw audio signal. Is it visible?
Huh,
Okay.
it is.
Okay. So, this this waveform, what I was telling you, I drew here, na? This was the waveform. Now, what I mean to tell you is that let's say this is a footstep. So every sound has a different pattern, right? Sneezing. So if you talk about footsteps, like tuck, 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 so it's a constant tuck, 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 tuck. You can see it from the waveform. Similarly, sneezing is a very impulsive sound. Like it occurs and then everything is stopping. So it is an impulsive sound. Then comes the church bells. Church bells are very loud usually. So you can see the amplitude is very high. Like the the data is more concentrated here, right? But it is covering the whole area. That means the loudness is also there. So you can refer to these kind of features from the waveforms, but still we want the computer to learn. So this is how we calculate the MFCC. You can see the MFCC is very different from different for every class. See the footsteps, it's very consistent. Then comes the sneezing. Here you can see some coefficients. Others are more like plain. Then church bells is completely different. Then comes the toilet flush, drinking or sipping sound. So also you can now see the spectrograms is this. It is very like you can see there is no energy when the sneeze stops. So everything is just silent. Silent means low energy, and low energy we know that it is represented using dark color. So you can
Ma'am, my
also see.
screen is frozen again.
Sahil, I am also looking at my screen. I mean, at my end it's working fine. Might be a problem with your internet.
Okay, ma'am, maybe I'll rejoin.
Yeah,
Uh,
please,
just a
please.
second.
Yeah, sure.
Yes, ma'am, I can see.
Is it better now?
Yes, ma'am, hopefully.
Oh, okay, great. Okay. So as I was saying that you can see the visible difference between the patterns observed here in different sounds. Like these are the features. That's how we differentiate in the given between different sounds. So this problem is called acoustic sounds classification because it's not something related to speech. However, in speech also these kind of features are used. Let's see, this is called a chromogram. Chromogram. Um, like MFCC is one feature, tempogram is one feature, spec is one feature, MFCC is one feature. So different features can be extracted for the given audios, and then we can feed it into a deep learning system, right? Um, so okay, so a spectrogram is basically a visual representation of frequency content over time. So the first option is a plot of amplitude against time. No. Second is correct. Third is a measure of signal power over time. No. A representation of phase information. No. So second is correct. Now, in the context of operator safety in complex heavy machinery operation, how can voice analysis be utilized? This is more related to the effective computing aspect. It's less of a technical question. So, to control the speed of the machinery, to monitor the environmental conditions, to assess the state of the driver or operator, to detect physical defects. Voice usually refers to human voice, right? So if you are able to capture the driver's or operator's voice, then you can detect whether the driver is in the right state or
Mm.
not. As in, as in, the voice analysis can help us in operator safety. Let's say we can also detect if there is any kind of fatigue or drowsiness. Let's say changes in speech pattern. Your speech might be more, more heavier when you are sleepy, or slow response time, or the speech pattern changes than usual. So you can say that it indicates fatigue or drowsiness. So if an operator sounds tired, then we can alert, or we can just stop operation for a while. And this is useful in the high risk environments. Second is monitoring stress and anxiety. Let's say increased pitch, irregular speech rhythm, tremors. You sense in the voice. Then we can detect the stress levels and suggest some breaks. Also, we can identify cognitive load and distraction. Let's say the operator hesitates or struggles with the speech clarity, then we might say he's not focused in his work. So we can tell that okay, you need to focus more because this is a very sensitive. Let's say you are you're picking up some heavy load and you have to be very careful not to drop it. So it might actually cause very much damage, so it can be in a high risk environments such as mining or construction or aviation. So we can, I mean, use these kind of systems. So yeah, to assess the state of driver or operator. The first option is to control the speed of the machinery. No. To monitor environmental conditions. No. To detect physical defects in the machinery. Physical defects are something like you can say that if we can capture the sound of the machine and then it is an abnormal sound, then we can say might be some problem. But here we are talking about the voice. Voice means the human voice. Next question is, voice analysis is not as effective as facial expressions in determining emotional states in affective computing. What do you think?
Ma'am, I think true.
Um, we cannot say it's true because these two are different modalities and it can complement each other. So voice analysis can be just as effective as facial expressions. So one benefit of using voice-based analysis is we cannot fake our emotions in voice as compared to we can fake our expressions. So you are suppose very nervous. So you can always put a smile on your face and fake your confidence. But then if your voice is very much like trembling or so, you cannot control it. So it is a better indicator of you being under stress. Voice analysis can be just as effective or even more in certain scenarios, like I mentioned. And it provides, like, while facial expressions provide us visual cues, voice analysis can capture auditory and acoustic cues that sometimes are more reliable, especially when facial expressions are intentionally suppressed or ambiguous. So, how does voice analysis help us to for the emotional recognition problem? Firstly, it captures subtle emotion variations. Let's say the tone, pitch, speed, rhythm of the speech, and even when facial expressions are not indicating anything, they're neutral. Maybe a person may force a smile while their voice still reveals sadness or stress. Then works in non-visual conditions. Let's say the lighting is very poor. The camera is not able to capture well. However, you can capture the speech and then you can sense it. When the person is partially hidden, voice analysis is more reliable. Let's say call center AI detecting frustration in customer's voice, right, without seeing their face. Then it is harder to fake, as I mentioned. It is very hard to fake a voice pattern as compared to a expression, an expression. So it is false.
Ma'am, but like people do impersonations and like if you're like sad but you can sound excited,
So
like people like
impersonation is not this, we can say it's not under this jurisdiction. We are talking about affective here. So emotional, even if we can fake it, definitely even the data sets are collected like that. They are called acted data sets. So the actors are told to be like, give a happy expression in your voice. So they are trained to do so. But usually when we are just only talking about is it effective or not, then we cannot say that it is not effective. It can be as effective, even sometimes more effective than the facial expressions. Faking is always there. Fake can even I personally work on defect detection only. So that means people try to mimic others' voice, a spoof, create spoofs. So that is a
yes,
different
ma'am.
research area. Exactly. So that is a different research area. But here we are talking about only the emotional emotion detection. So the question is just comparing between facial expressions and the voice. So whichever is better.
Ma'am, like if the same question was like reverse, like
Hmm.
facial expressions are not as effective as voice analysis, so then what would the answer be?
Um, you can say not as effective. We cannot like say absolutely one modality is better than the other. Still, I think I would go with false because it depends on the context. It depends on the situation. There might be some situations where the person is not speaking at all. Like suppose you're capturing the reaction of audience, right? So also in the case of neuromarketing, have you ever heard the term neuromarketing? What it means is that
No,
let's
ma'am.
say you have an advertisement, you're in the creative field, or you are a producer of a movie, let's say director, sorry. So what you want to know is that okay, I have created this advertisement. I want to see how people are reacting to it. So how can you capture? One way is that you call people to your place, to your office, and then show them and say, okay, tell me the feedback, give me the feedback. This is a very tedious task. So in this computer vision era, what we can do is we can just broadcast like in an experiment and tell people to take part in the experiment, and just you have to watch it and your facial video is being captured. Now you don't say anything. Watching a video, you're not saying anything. So voice does not come into the picture. What you're doing is essentially capturing the reaction, facial reaction. Let's say there is an advertisement which is designed to be very funny. So is the person laughing? That means the person is happy. So you can capture it and then you can analyze it. The person is feeling happy, or maybe if I find the joke cringe, I might do like disgust. Like what are they saying? Or some what I mean to say is that in some cases the voice might not be available. So you cannot say that absolutely better than the other modality. It depends on the situation. It depends on what circumstances are there, what the application is, what you want to analyze. So I think I would go with false even if the question was reversed.
All right, ma'am. Okay.
Hmm. Okay. Then considering meta information about a user's background and culture is unnecessary for understanding emotions through voice in effective computing.
Ma'am, true.
Okay.
Oh
So
no, actually false. No, ma'am, because their cultures,
yeah,
it
we just
explained
discussed that.
earlier,
Correct.
like where
So
he comes from. Yeah.
exactly. So same points here because different cultures express differently. And in Western cultures, it is very okay, pretty much okay to express freely. The men, like let's say typical example, men don't cry. So men can it can be considered good that the person is more empathetic if a man is crying. However, in Asian typical society, if a man is crying, it can be considered as a sign of weakness, which is not the case. I mean, you cannot judge like what context is there, right? So if you know the context also, if you know the background, then you can better be a better judge of what is being expressed. So let's say different cultures express emotions differently. Some cultures encourage expressive speech, while others they don't want to express much. Okay, in Western cultures versus Asian cultures. And language specific speech patterns are also there. There is a specific tone in English. Let's say I am very surprised. Oh, I would say something like, "Really? Like that happened?" So it is more of the tone. However, in Mandarin, it might be just the variations. I don't know Mandarin, so I cannot give you an example. But just for the sake of it, in Mandarin, different variations may change the meaning and not the emotion. Right, so context also matters in emotion perception. Let's say an AI model which is trained on American context, it might fail to interpret what is being conveyed in a Arabic or Hindi context, right? So this is false. Okay, what is the concern regarding simulated or acted data in emotional analysis dataset? I really want you to answer this one. It provides the most accurate representations of the real-world user behavior. Not all examples captured may reflect genuine user behavior. It is easier to collect compared to other data, and simulated data is less prone to biases.
Ma'am, I think they may not reflect genuine user behavior because, like you said, people
Yes,
impersonate it.
yes, because we are telling them to uh, express in a certain way, and it is not a real world situation where you are actually, let's say your friend is surprising you with a gift, and then what your reaction will be, you will be genuinely surprised and very happy, and then how you will express. And suppose a person is telling me that now you have to act surprised, so there's a huge difference between acting surprised and actually being surprised. So maybe happy I can mimic correctly, but not the other expressions. How can I mimic depressed? It is very difficult. So it might not reflect the genuine user behavior. And what are the problems associated is acted can be like over exaggeration of emotions. Let's say even if I'm happy, like I don't smile much, but if a person tells me to be happy, I might over exaggerate my and fake my expressions. And it is less representative of what natural emotions, because natural might be more subtle. Then, similarly, second point is again lack of subtle and spontaneous emotions. Genuine emotions are also like sometimes micro expressions. In previous sessions, we discussed micro expressions. Let's say micro expressions, what they mean is when you're genuinely experiencing something, and even if you like try to suppress, okay, I shouldn't laugh in a serious situation, but some lip movement can be there, and somebody might be able to spot that you are trying to suppress your laugh, because it is a very minute change in your, but you can see a subtle smirk or something. So this comes under the you can say micro expressions. So in genuine situations we are also having these are involuntary, but here if it is acted, then micro expressions are not being captured. And then differences in emotional triggers. I'm of course, in like I mentioned, if you are actually getting a gift from your friend, and then you are like expressing it, it's very different from the what I'm telling you, like to mimic. Let's say person is genuinely frustrated, like a they are receiving constant calls from customer service, and then it might sound very different from an actor who's trying to be frustrated. So yeah, correct answer is the second option. Huh. Next is confirmation bias is the tendency to interpret information in a way that confirms one's pre-existing beliefs.
Ma'am, I don't know
Okay.
this.
So confirmation bias is what happens is, so since we are studying affective computing now, Sahil, so it is a combination of different concepts from philosophy, CS, and more like we also talk about something more related to the cognition. Cognition is uh, the ability of your brain to process things, like how fast you can process things. So cognitive bias, what it means is like you are biased towards some things, right? We favor some things, we interpret in our own way, and we recall what we want to recall. And we usually do these things which supports our pre-existing beliefs or opinions, right? And we ignore, or we literally we want to erase the memory of something which does not align with our uh, mm, beliefs. Let's say we India versus Pakistan, there are matches, and then you will remember where we won, but you don't want to remember where we lost. So we want to keep those happy memories or selective memories with us, and in this case, like, we have selective attention as well. Like, people tend to focus on information which supports their views while ignoring alternative perspectives. Let's say somewhere who believes in a particular diet only reads studies that support it. I might not want to read anything which says against it. So then there comes selective interpretation. Let's say there are two people and then same stimulus is there, but then they will understand it or interpret it in their own ways, because they are, like, if they are watching the same political debate, you might think that person A was better and the other person might think person B was better, depending on your biases. Then selective recall, as I mentioned, we want to remember information that will support our views, and we don't want to remember anything that contradicts our views. Let's say who tells us like astrology is actually it is very accurate, then he or she might recall only those incidents which proved right, but then they don't tell us about something that was wrong. So yeah, in effective computing, how can we say that the confirmation bias is impacting us? Let's say an AI system is trained to detect emotions in job interviews. So in effective computing, what essentially we do is we make the computers, we make the systems more intelligent, and intelligent in terms of emotions. Let's say you have Alexa at your home. So you talk to Alexa, Alexa play this song, Alexa do this, Alexa. But then Alexa is very, it seems very robotic. But if you want to talk to them and let's say you sound very low today, and Alexa responds in a way that, you know what happened, Sahil, you seem to be very low. So it will be more relatable. We will feel very good about it, that okay, this device is actually able to understand what I'm feeling, and you might be able to feel better. So even Alexa might start playing some happy songs to cheer you up. So this is what we aim to achieve in the whole affective computing domain. And in other applications, let's say job interviews, so you want to select some good candidates out of, let's say, 100 you have shortlisted. Now you want to ease your task by assigning first round will be a computer interaction. So the computer assesses you and then tells which candidates are better in the term, in any terms, whatever you want. Then let's say an AI system is there for job interviews. Then if the training is happening in such a way that we have only used Western individuals, and they are usually smiling while answering, or it is smiling is considered as confidence or friendliness, but in some cultures a more neutral or serious expressions is more encouraged. So let's say the model classifies any smiling as overconfident or something like that, or neutral, or even if the person is not smiling, then they consider it as rude. However, it is very normal for, suppose, Indian people to not smile while they are being interviewed. So different interpretations are there for the same thing, same smile. But since the model is having a bias, which is confirmation bias, then you cannot use a system which is trained on American data on Indian people. So that is where this bias comes into picture, and that is where it impacts. So this is
Ma'am,
true.
like, how do you solve this issue?
How do we solve this issue?
Yes, ma'am, that because of the bias, like the
Yeah.
incorrect,
Huh.
yeah.
So usually what we do is we want to use better data sets, better quality data sets. Let's say you want to use a data set which includes every race, gender. Let's say men and women can also have some differences. So you make sure that you include data, everything. Like, okay, machine learning models or deep learning models are nothing but whatever you feed the data, they will learn patterns according to that.
Ma'am, so like a more diverse sample
Yeah,
data
so
set.
so it depends on the quality of what data you are feeding into it. If you're just feeding American people's data, then it will learn only about that patterns. If you're using a combination of different ethnicities, different race, gender, maybe economical backgrounds or whatever, also demographics, basically different demographics, so you will be able to achieve a more generalizable outcome, a robust systems. So if the model has earlier seen something which is true in the context of Asian people, then it might be able to better recognize in the inference time. So the solution is to use better quality data, which essentially translates to including more types of or more comprehensive or inclusive data. So, okay, ninth question is, what is the purpose of conducting statistical analysis on labels generated by multiple labelers for same samples in a database? So this basically talks about the data collection task. Data collection, sometimes what we do is we want to collect some kind of data set. So data set is essentially having the feature values, and then there is a true label, right? Let's say I want to develop a system where I want to say that, okay, uh, I am showing you a video. Is it neutral, happy, or sad? Now, I have captured a video. I show to 10 different people, which are my reviewers, right? And then multiple labelers, I mean. So, labelers, I want polls from everyone. So, what will be the majority? Then I will say that is video is, let's say, the out of 10 people, 8 people say that the video seems to be happy. Then you will say, okay, the video is happy, and you will assign the happy label to it. And similarly for sad and neutral. Now, let's say the labelers are, but how do we check that the labelers are actually correct? Like I might, मेरा mood आज ठीक नहीं है, so I might not be able to uh, assess it correctly. I might not even pay attention while assigning the label. So maybe the quality of the data, it degrades. So I hope you're getting my point. Like you, for training some models, you need good quality data. Good quality data means that it is correctly labeled. Now, depends on personal or whatever reasons, the how do we check, how do we maintain the quality of the labels assigned, because different people, we also need to check on those labelers that you are doing it correctly, right? But you cannot influence it. That also is a concern. You cannot tell, okay, this is happy, and why are you not labeling it as happy? Because that will be your perspective, not the labelers. So you cannot tell them to correct the label or whatever. But then you also want to make sure the person is doing it fairly and honestly. Now,
Ma'am, is this not about like, for example, if like a particular data set has like three labels,
hmm,
like two labels, happy and sad,
hmm,
but and like that's from one labeler, and
hmm.
another labeler says the labels for this data set are happy, sad, and neutral. Like for example, so ma'am,
Hmm.
does isn't this talking about that, like the different labelers assign different labels, or am I wrong?
So yeah, I mean, you
I
can't.
understood it as that actually.
Yeah, so let me just tell you. Let's say in a data set there are 10 videos. And every video can have one label out of the three. Let's say you can have happy, neutral, or sad. Now, person one, this is before the development of models. We are just creating the data set, so we want to provide the ground truth. Now, ground truth, how do we decide the ground truth? Let's say I have three labelers, and the person one, I show him the video one. The person one says, I think this is a happy. Then the person two says happy, happy. Okay, good. No contradictions. It's fine. Then video two. This person says happy, but the other says sad. So I will assume that this is sad, the majority or whatever. Then comes this. But then I'm not talking about this thing. Like this is just I can take the majority and then I can assign the sad label. But then I also want to make sure that whoever this person is, they are participating honestly. Like I uh, let's say I want to make sure that you ask your friend to label it for you. Now your friend is actually participating, and sometimes what happens is you have to fill a form. You just tick tick tick, all options A are correct, and then you just go submit it. But this should not be the case, because otherwise, let's say there is a video which is actually happy, but this person is very lazy. They don't even want to. The person is labeling everything happy. Right, but the video was actually sad, so other are correctly like labeling it as sad, sad, sad like that.
Oh, ma'am, so this is labelers are basically the people who are participating in the survey,
No,
who are like
uh, yeah, we can say that. Yeah, the people who are
who are
participating.
deciding whether the video is happy
Yeah,
or
yeah,
sad.
yeah.
Like
This
they
is
are
the
doing.
first stage of data collection. So you're collecting the
Ma'am,
data. You are,
so in this, like in don't we do that? Like we try to remove the like the inconsistent parts, like the people who have, like you said, the lazy people or the people
yeah.
who
So
haven't
how do you
put
know
forward.
who is lazy, who is being lazy? We don't know them. Like
Ma'am,
how.
so I think data cleaning or something
Yeah,
like.
data cleaning, but see, there can be more complexities in that. Let's say I personally think that the video is sad. I might be having my perspective. That does not make me lazy. If I'm differing from the rest of the labelers, that does not mean that I'm lazy. Maybe I have a different perspective, so you also have to take care. But then how can we decide that the person is actually paying attention or not? There is one method, and it is called like labelers agreement. Is like when multiple labelers annotate the same samples in a database, statistical analysis is conducted to measure agreement. There are two types of things here. Number one is that person one, person two, and person three all are like agreeing on something. Then we also calculate something called, let's say, uh, the thought process of P1 and P2 match really well. So mostly they will have the same labels for most of the most of the samples. Only maybe one is differing, but mostly their thought is matching, right? But P3 is very different from there. So what we can do is maybe later analyze what person is behaving like that. This is one thing. This is called labelers agreement. Then other thing can be that how do we decide that a person is not being honest and honestly labeling. You can do just a simple trick. You show them video one, ठीक है? You show them video one, tell them to label it, and after like 10 days, show the video again. Don't tell them that you already have visited. Let's say initially he mentioned this as happy. Then the person should also mention the same video again as happy. Then that means the person is actually paying attention. ऐसे नहीं है कि randomly is assigning the labels. So this is also an important thing that this is how we figure out. And let's say the person is, you show them three times and every time he is assigning a different label. That means the person is not reliable. So you can skip that. Got it?
Oh, got it. Ma'am, in the first one, you said like if P3 is different, then
Hmm.
what do you do exactly?
P3 is different than, so it depends on you. Let's say, mm, वैसे तो नहीं करते हैं कुछ, because person has all the right to be differing in their opinion, but since we are taking
Hmm.
the majority, so ultimately only one label is there, and in the data set that we get usually to use, We don't have any this P1, P2, P3 labels. We have only a single label, which is decided based on some kind of majority measure, like something like maybe voting or majority. Let's say out of three, two are agreeing to some. That's why we take odd number usually to break, have a like whenever there is a tiebreaker के लिए we have odd number of this labeler. So anyway, one
Okay, ma'am,
category
so
is going to.
just on majority, just for
Yeah, majority.
majority.
This is
Okay.
just one way of doing it. Maybe if this is a class label, let's say there is some kind of value, then you can take an average of the value like that if it is a number, right? So there are multiple techniques. So the question was that what is the purpose of conducting these statistical analysis? We want to identify the inconsistencies and discrepancies in the labels, right? So when multiple labelers annotate the same samples in a database, statistical analysis is conducted to measure agreement, detect inconsistencies, and improve the label quality because label quality decides how well your model will behave. And then we want to make sure that our dataset is accurate, reliable, and unbiased. And yeah, so one labeler, like these are just examples, detects labeling inconsistencies, and this can be one labeler can assign a neutral face as sad while other can mark it as neutral. So this is inconsistency. Then interrate interrater agreement. Interrater agreement is what I just mentioned here. Like P1 is agreeing more with P2 most of the time. So P1 and P2 have higher interrater agreement, and while P3 is differing. So this happened in my personal experience as well. Like I assigned some labels, but it was different than rest of the people what they were assigning. So three people were assigning me and two others, but the two others their labels were matching more than mine. So that means they have more agreement than my labels. And then higher agreement means more reliable. That means if many people are saying the same thing, that means it is trustworthy. Then what it does is it improves the dataset quality. And majority labelers mark an expression as happy, but then one labeler can mark it angry. We can use any kind of statistical mean, median, majority, then you can use it. What it helps to do is reduce the biases and increase models fairness. So yeah, second is the correct answer. Okay, in the context of feature selection for emotional analysis, what is suggested approach to achieve balance between different attributes of the signals? So feature selection, how do we proceed with that? Using a single feature for arousal and balance, selecting features randomly, or applying fusion techniques, ignoring feature selection and relying solely on raw data.
Ma'am, fusion techniques.
Yeah, so what we usually prefer is we don't want to miss out on any kind of information. So let's say one feature captures one kind of information. So since you missed the previous lectures, any emotion can be represented using two things. Let's say if any point is there, you represent it using x comma y, right? So x comma y in case of emotion can be valence and arousal. What valence means? How happy or sad the emotion is, and let's say here I can draw. This is called the valence, and this is called the arousal. So valence means positive or negative, मतलब happy or sad, positive or negative, and arousal high or low. So let's say you're saying relaxed. Relaxed, where will it lie? This is relaxing is a positive activity, right? So you can say that relaxed will be on this particular region.
On
Let
the
me highlight.
top right.
So this is a positive valence area, and there this is a negative valence, right? This is something like okay. Let me mark this. This is negative. This is positive. This is also like high, and this is low. So relaxing is a positive activity. But then are you excited or are you not excited? You are calm. You are more on the calmer side. So it is negative on the arousal side. So we can say that relaxed might somewhere lie here. in this quadrant. Understood? Let's say uh, what can anger. So anger is a negative emotion, right? Negative side. So it might somewhere lie
Yes.
here. Anger will be lying here. But is it a high arousal state, or are you calm, or are you aroused or excited? So we are more
Hi.
high arousal state, more excitement. So somewhere here anger will lie. That's how you represent the emotions, and then you can definitely have some kind of value for valence, and like x comma y for valence and arousal. This is how we represent the emotions. Now, uh, one set of feature can be able to capture the valence more, and other might be able to capture the arousal. Let's say I look at a person's face. Now I can capture the smile, right? Or I can capture the frowning. But then I cannot tell the excitement level, whether it's high or not, right? Let's say I'm talking about relaxed and neutral. So relaxed means lower excitement than the neutral state. ठीक है? So just by looking at someone's face, both expressions will be same, no expressions at all, like very neutral state. But in relaxed, the my blood pressure might be down, my heart rate will be low as compared to neutral state. So you can capture this using heart rate monitors or maybe skin conductance. So these also we discussed in the previous sessions. There are multiple physiological methods to capture. So let's say some features which are better at capturing arousal can be there. Let's say pitch. I'm very excited about something. My pitch might be higher side, and heart rate might also increase. But then if I'm in the relaxed state, the heart rate will drop. And some features are more like better at capturing the valence only. So like facial expressions can be a better measure of how good or bad you're feeling, or how pleasant or unpleasant the feeling is. So we can always use complementary information, and even in many deep learning methods, feature fusion helps to gain performance, gain performance. Let's say accuracy is increased. And there are multiple fusion techniques. First is early fusion. Early fusion means that if you know about deep learning systems, then we have some features. So features can be combined first, and then the model can be trained on combined features to produce an output. Then late fusion. I have a model which works on let's say facial expressions, and other one works on pitch. Other one works on pitch. And then two models, they give their own predictions, and then you take the majority or voting or average or whatever you want, and then you predict something that is called late fusion. Then there might be other methods which can use multiple modalities in a hybrid fashion as well. So you want to anyways maximize the performance, so there can be multiple fusion strategies. So this is the correct answer. Now, which of the following statements is true about F naught? F naught is the fundamental frequency. It is the frequency at which vocal cords vibrate in voiced sounds. It is the musical pitch of the note that is perceived as the lowest partial present. So I'll go to the uh, description. Fundamental frequency, like I mentioned earlier, whenever we are talking on whenever you're playing a key on a or note on a piano, it is not a single frequency. What happens is, let's say you speak something. So uh, this is a frequency, let's say 10 hertz. So 10 hertz, suppose you have a certain pattern like that. Like 10 hertz is there. Then this is the base frequency that is there. Then on the higher side, you can also observe that multiple of this particular frequency, like 10 into 2 is 20, then 30, then 40. Some faded version, I would say, like this will also be there. But then the intensity keeps on decreasing. So the majority of the voice has this component. Then slowly, slowly, like just a faded version of the same pattern. And so one more way to understand this fundamental frequency, let's say there's a keyboard. If you have ever played a keyboard, there are so many blacks and white keys, right? This is something like this. Uh, Something like, so there are so many what we call as octaves. Uh, One key here, C, can also, it also repeats a pattern, right? So another C can also be there, but the octave shifts. So that means they have same sound, but then one is more shriller, one is high pitch. So as you go towards the end of the piano, the sound becomes more shrill. But then ultimately the sound is same, right? So if you play both sounds at the same time, it will sound somewhat like only a single tone, but then it contains multiple frequencies. So this let's say C1 and C2 are kind of multiple of each other. Let's say this, suppose this is 50, then this will be 100, and then there will be another C3 that might be 50 into 3 is 150. So like that, it goes like that. So, but the base one is 50. So this one we will call it as a fundamental frequency because this is the base, and then everything else is just uh, the multiples of that. So they are called like harmonics. Harmonic one, harmonic like that. So at a periodic waveform repeats itself, it's called it forms the basis of pitch perception of a sound. So whatever you hear, you you recognize a person's voice through the characteristic which is called as pitch. I have a different pitch than you. So but in speech production, what happens is since we produce the sound from our vocal cords, the fundamental frequency is associated closely with the vibration of vocal cords within the larynx. This is a voice box, and what happens is that the lungs pump air through this pipe, and then the vocal cords are like they form different patterns. Let's say this is the windpipe, and then air flows like this, and then there are vocal cords. What happens is if they if they form a pattern like this, then different sound will be produced. If they form a pattern like this, maybe this, then different sound will be produced. So depending on how you are controlling the vocal cords, how they're forming a shape, it kind of impacts the output sound that is being produced. So that's how we are able to produce different sounds, and also the mouth movements as well. So the rate of this vibration determines the fundamental frequency of the sound produced. So this is a whole, like you can see here. So this air flows from the lungs, and then vocal जो cords होते हैं, vocal cords, they are forming something, some shape, and then we are also modifying the sound. Like if ever you want to say k, you have to say in a certain way. Your tongue and cheek will have certain pattern. Similarly, then the speech signal is formed. Yeah, you can see here in any speech pattern. This is also showing you the same thing. Like it is the pattern is repeating. That means this F1, F2 peaks you can see, and this will be multiple of each other. So this is how it works. In music also that I mentioned, let's say fundamental frequency of 440 hertz, it is perceived as musical pitch A4. So 440 is A4, like 110 will be A1, 220 will be A2, like that. And the fundamental frequency is why it is fundamental because it determines the pitch of the sound. Then it is also measured in hertz. So both A and B first talks about the sound voice, and second point talks about the musical notes. Okay, which of the following are examples of prosody features? Prosody, as I mentioned, prosody is the way of speaking. Like I have a certain style of speaking. I use this tone. Uh, let's say I use a certain tone. Your teacher might have a certain style of saying something, and we usually mimic those style to mimic their voice. Um, like say Amitabh Bachchan, he has a certain style. He will say Devio or Sajjano. So he has a certain style. This is his prosody. Like and similarly, what kind of features that are there to describe the prosody? How do we describe a person's characteristics, voice's characteristics? So prosody refers to the patterns of rhythm, intonation, stress, and timing in speech. Some person might speak or might talk too fast, but some are very slow. So it also includes in the prosody. Prosody encompasses the melodic and rhythmic aspects of language, and it plays a crucial role in conveying meaning, emotion, and emphasis. And yeah, it includes rhythm, intonation, stress, pitch variation, pauses, etc. So common prosody features include the pitch. Pitch is like fundamental frequency. So prosody feature, it represents the lowest frequency of vibration of the vocal cords. Then it tells us the formant frequencies are also there. Formants are the resonant. Just like I mentioned, harmonics or resonance is also called like it is also a similar concept. So resonant frequencies of the vocal tract are also the result from shaping from the vocal tract during speech productions. Let's say formant frequencies such as first and second formants are important for distinguishing vowel sounds and also considered prosodic features. Then phoneme rate. Phoneme rate is basically at this frequency or the speed that you talk or different speech sounds occur. It also indicates the rhythm and timing of the speech. And overall prosodic pattern is determined using these features. So all of the above, they represent prosody. Okay, dataset presented by IIT KGP SESC is an example of. This was mentioned in the slides in the lecture itself. If you have attended, then you will be able to answer. So this a speech data base for analyzing emotions. It is present in the speech signals, and the proposed database is recorded in Telugu language using the professional artists from All India Radio. And total of 10 professional artists have contributed, and this is collected by simulating 8 different emotions using neutral sentences. So let's say I'm going to the market. This sentence itself is a neutral sentence. There is no emotion attached to it. I'm going or I'm going to the market. Now, you tell people that you have to say this in a happy tone. Let's say, hey, I'm going to the market. Then, in a sad tone, I'm going to the market. This is more of a sad tone. So, that's how you collect the data. This is exactly what we were talking about, that this is more of a acted or simulated, this is that kind of data set. So, this is named as IIT Kharagpur Simulated Emotion Speech Corpus, that is SESC. So this is not a natural data set, this is a simulated data set. So we will also learn about this natural induced simulated. Natural is basically you are capturing something which is happening on its own in the most realistic settings. Let's say there are people in a cafe and you interview them, and then you capture like people are laughing, and induced is you provide them some kind of stimulus, and then their the reactions are genuine, but the stimulus is what you intend to induce. Let's say you are making them watch a funny stand-up comedy video, so they will laugh only. So you record the laughter, but you're inducing that through a stimulus. Then simulated means to mimic something, right? And then you're mimicking, and this is more of an acted data set. Okay, next is speech rate signifies. Speech rate means loudness, pitch, voice quality, or velocity. So as we can
Velocity.
Yeah, exactly. So speech rate means how fast you talk. So it is exactly the velocity. Loudness means the volume or the intensity of the speech. Pitch means your like fundamental frequency, how your voice characteristics it is a more of a voice characteristic than voice quality. There are like how husky or how shrill your voice is, and it's not directly related to speech rate. So velocity essentially means how fast do you speak. So D is correct. Okay, I'm going skipping these questions, like I'm going too fast because I have a lot of questions to cover and I want to cover. But if you are not comfortable at this speed, you can tell me and I will repeat it. Okay, angry speech has a higher fundamental frequency, true or false?
True.
Yeah, because usually when we are angry at someone, then we tend to shout and our voice becomes more shrill and uh, but it is not a hard and fast rule, but generally we observe that the voice becomes relatively shriller. So angry speech can sometimes be associated with a higher fundamental frequency, especially in intense or aggressive expressions of anger. And because why does this happen? Because of some physiological changes, let's say increased muscle tension in vocal cords, resulting in a higher pitch. While it's commonly believed that angry speech might lead to higher, but it's not universally true, right? Some people naturally have higher pitch. That doesn't mean that they're angry. So it's not, the converse is not true. But yeah, usually this pattern is observed. Okay. In iterative feature normalization, observations that are labeled as neutral are used to re-estimate the normalization. This is a very long discussion this is going to be. So yeah, I will go on with the discussion. What happens is that whenever we are trying to train machine learning models or deep learning models, what we require to do is to normalize features. Normalize or standardize. Normalize means that let's say I have two features of the house prices. Let's say this house prices, or let's take an example in the affective domain only. Let's say we have EEG values and heart rate values. So let's say this is in the form of minus 1.523, this is minus 2.37, like that, and heart rate is typically 80, 70, like that. Okay, and these two are features and we want to predict something. However, when you directly feed these models with this unnormalized data, it is very difficult sometimes for the model to understand that what is this, like 80, it is different range going on, and this is minus different range going on, but that does not mean that this is less important and this is more weightage, right? The numbers don't represent the weightage. So usually what we do is, it's a good practice that we want to bring everything in a same or similar range, so that let's say I normalize EEG values, I do some use some maths and bring it in the value point. Let's say this is point 0.5 and this is point 0.7, and then and heart rate also I brought to the same range. Let's say this is point 0.8 and this is point 0.2. So now you're able to guess or understand it better, that how it is relatively. So now you can see that okay, this is more on the higher side and this is on the lower side. Where same, this is on the lower side and this is on the higher side, right? So you're, for better understandability, more the model might also be able to understand it in a better manner. So it makes the learning more better, faster. That's why we usually do the normalization. Now, there are multiple ways of this normalization. What happens is that usually when we talk about emotions, emotion recognition data set, so we discussed about these different features. Let's say there are features, this is fundamental frequency, right? And other features might be, let's say, EEG or okay, any other feature, let's say. Now, we want to predict the emotions being conveyed. Um, in F naught, let's say there are people, this is speaker 1, speaker 2, and this is male and this is female. So usually females have more shriller voice and men usually have more hard, like heavy voice. So fundamental frequency for this person will be lower. This will be lower than and this will be higher. But that does not mean the females are always angry. Like this is not the case. So this is all the values of the person will be according to the demographics, or it will be very much dependent on what is the age of the person, what is the gender of the person, and what other like factors might be there. So we need to normalize, like let's say this value is 10 and this is 20 and then this is 30, and similarly this might be 5 and EEG might be 20, like 13, whatever. So essentially, we want to normalize this according to this person's characteristics. What I mean to say is, let's say there are two persons, P1 and P2. Some people are more like they sound more aggressive, even if they are neutral. Let's say even if they are neutral, इसकी neutral की value will be 50 for some feature, but for this person neutral's value is 100, right? That does not mean the person is, but this is also neutral, right? And then angry, this value might increase to, let's say, 150, and this might increase to 200. But then you want to normalize. If you use a standard like divide everything by 10. Let's say this is a normalization criteria. Divide x by 10. Now this becomes 5, this becomes 15, this becomes 10, and this becomes 20. But still, there will be some kind of discrepancy. This value is still higher. This value is still higher than this person. Although this is the same emotion being represented, like this is neutral, this is angry, neutral and angry. However, the values are very much different range is there. So what we want to do is like we should normalize according to the speaker itself. So let's say uh, we are talking about the initial values only. P1 is P2 is there, then um, it was 5 and 50 and 150 and 100 and 200. So you take this as base, and let's say you take the relative difference. So relative difference becomes 50, and this is 100 point difference, and same, this is also 100 point difference. Now they both are on the same page. We can say that the both are on the same page, because earlier it seemed that this person is more on the neutral side because they're lower number, but this is more aggressive, but not, it was not the case, right? But now you can see that according to the baseline, everyone has their own baseline, so you can compare accordingly to that number only. And without normalization, we just saw that it's not that effective, that it might cause some discrepancies. And then for normalization, there are multiple methods. Now, there is a method called iterative feature normalization, and the other method is called identical feature. That means identical means you use the same technique for everyone. Let's say the thing that I mentioned here, you divide everything by 10. That means you are applying the same method to everyone, irrespective of whatever is happening. But it still is maintaining the ratio, right? 50 is becoming 5, but then 200 is becoming 20. So you won't be able to grasp the difference between the two. Can you just tell, like, if a value is 50, then is it higher or lower? It does not, you cannot have any information because you don't know about what kind of person is this. Is it a female? Is it a male? Or what is the age? So ultimately, ultimately you want to know some relative information, relative numbers according to that person only. That is where iterative refinement also comes into picture. Here here in this example, you knew that what neutral for me means my Akanksha's neutral value is 50, whereas Sahil's neutral value might be 100. So in this case, we knew the neutral values, but in this new real world scenarios, what happens is in most of the data sets, we don't know the baselines. So we want to firstly go without any normalization. The model will not be that good. Firstly, we are without going without feature normalization. We just use an existing system to classify. Then we get the emotional labels and neutral speech. Now, neutral is what our baseline is, right? Then we separate out the neutral speech. Then we kind of normalize it, right? Using the neutral speech. After normalization, then we again go through the same loop. Like we have estimated some normalization normalization parameters, then we go again with the normalization. So let's say initially I don't know about what my number is, what baseline number is, but I have the other data. So maybe one value is 50, 100, 150, but in your case it is 20, 25, 30. So my range is very different than yours. Now you want to normalize. So I will observe my data and try to classify my speech as neutral, emotional, and then I can use neutral one as my baseline. So basically, repeating the same process again after normalization, the performance should increase. And after so many iterations, if the labels are not changing anymore, that means we have reached the saturation. This is the iterative feature normalization. This is very complex to understand in, I think, first go, but I hope I tried to give some examples. But even if you don't understand, you can refer to this as later, and then, of course, in next session also we can try to discuss this. So, okay, I just mentioned the term identical feature normalization. That means applying the same thing to every number in the dataset. So can it adversely affect the emotion discrimination of the feature? Yes, because it is not taking care of different individual variability. Like I might be of different range while the other person P2 can be of different range. So usually it's not the best approach to work with. So it might be less effective. It provides a global normalization, right? And treats all samples equally, does not differentiate between subsets, maybe speakers within the datasets. It offers simplicity. It is very easy. It is very easy. You can just divide everything by 10 and normalization is done. But then it may not capture specific variations or characteristics present in different subsets. Here, subsets we can compare with different speakers and between neutral and emotional segments. This is because it might remove important variations in the features, and then it might be less effective in addressing variability introduced by different speakers' vocal qualities. So this is true. Identical is not that preferred, so it should be more on the iterative side. Okay, this is fine. So, which of the following are true? Positive voices are generally loud with considerable variability in loudness, have high variable pitch, and are high in first to formant frequencies. Second is variations in pitch show differences between high arousal and low arousal emotions and when compared to neutral vocalizations. So, first point is like positive voices are loud. Positive voices typically exhibit the following characteristics. First is loudness. They're often louder because negative might be high arousal might be loud as well, but then usually positives are more loud and they indicate higher energy in the speech signal. Then the loudness variability is also there because we are very, suppose you are very excited about something, you're telling me like I'm teaching right now and I'm very excited about it, so I will be more on the, like I have made so many variations. But then if you're tired and then you might be able to talk in a very blank tone, right? Plain tone. So yeah, then comes the pitch. Pitch variation is also there. I'm trying to explain things in a better manner using variations in the pitch so that you're more engaged. Then first to formant frequencies like fundamental frequency, you can say. Uh, they also represent the resonant frequencies in the vocal tract and everything. So yeah. Then arousal and pitch variations. High arousal emotions like joy, they typically have more pronounced variations in pitch. Like I mentioned, I'm very excited about something, so I might like use multiple, like more variations will be observed in the pitch, and as compared to neutral vocalization. On the other hand, the low arousal states like tenderness, they can exhibit smaller variations, which might reflect a more stable vocal expression. So both are true. Okay, to account for variations brought on by the speaker's vocal qualities, speaker normalization is applied. Would you like to answer this one now that I explained the normalization?
Ma'am, true.
Correct. Uh, because because as I mentioned, like every person might have a different range of those features. So it is always better to normalize according to that person only and then compare with the other person. So let's read this out. It normalization is applied to account for variations brought on by the speaker's vocal qualities. The normalization aims to mitigate differences in speech features caused by individual differences such as pitch range, timbre, speaking style. By normalizing the features across different, the influence of can be minimized, allowing more accurate and consistent results in tasks such as emotion recognition or speech processing. So true. Normalization is always good. Women's voice have lower fundamental frequency than men's voice. True or false?
False.
False. Because women tend to have more shriller voice. So more, higher fundamental frequency or pitch in their voices compared to men. And vocal cords vibrate at a higher rate than those of men, resulting in higher pitched voice. So typical range for men is this 52 to 50 hertz, while women's range is 120 to 500 hertz. Okay, what is the primary motivation for pursuing voice as a primary modality in affective computing? This is, I think, taken from the book. So, anyways, facial expressions are unreliable. Voice analysis can provide valuable information without observing facial expressions, or voice analysis is less intrusive. Voice analysis is more accurate.
Ma'am, B.
D, because it is more accurate. D or B?
Ma'am, B, because it doesn't require face to.
Yeah, like I mentioned in the low light setting or whenever you don't
Hmm.
have any mode to capture the facial expressions and voice can be easily captured. Okay, which scenario illustrates the use of affective computing in indexing videos? Indexing videos is basically, let's say, Netflix is organizing your different movies in different playlists, and then what kind of like what is the basis of forming those playlists? So how can affective computing
Ma'am,
be
you
used?
mean categories,
Yeah,
like the
categories
categories?
you can say categories, but how does it group different movies in a certain cluster? What are the bases? And keep in mind that we are using affective computing here. So how can affective computing help in indexing the videos? So is it like analyzing facial
Ma'am,
expressions in movies, identifying keywords, searching for videos based on emotional content, creating subtitles? Subtitles is gone because subtitles is translation, not this, or ASR, speech recognition, not the affective computing. So D is incorrect. But what about A, B, and C?
ma'am, based on emotions.
Yeah.
C.
So I mean, basic question. So a video, it can analyze the audio visual content to detect emotional cues. Let's say a movie is very happy, or a horror movie can induce fear. So, what you can do is like you can use the audio track, because in a horror movie, the track will also be like very thrilling or like that, right? Haunting or screams, these kind of sounds can be observed. But in more of a comedy movie, more laughter, like these cues can be observed. So then user might be able to enter keywords like happy or exciting, and then you can just group. Netflix can use some algorithm, some model to cluster them together. Suppose let's say happy movies are there, and then you search for happy movies, and then you get the corresponding movie list. Then, how is effective computing utilized in automatic translation systems? By translating between languages, by ignoring emotional nuances, by analyzing emotional and behavior aspects, by focusing on linguistic patterns.
Ma'am, emotional aspect.
So, B, right?
Yes.
So, it can be used. Not only the linguistic content can be analyzed, but then emotional behavioral cues can also be used. So that way, how can we like enhance the performance of translation is also always there, right? But then you can also get to know what is the intent behind saying that. It can be a sarcastic statement. So normal just translation won't help you to understand the sarcasm, but affective can help somewhere. Okay. What are the three major factors identified by Borden and others as challenges in understanding emotions through voice? What are the major factors? Speaker's accent, pitch, and volume, age, gender, cultural background, content, paralinguistic and speaker attributes, emotional state, tone, and body language. I suppose that let's just go on. So three components is uh, the content, what is being said. So the if I'm saying that, oh wow, I really like this gift, that means this is more of a surprise, happy tone. And automatically, if I only just use the text only to analyze, I can guess that the emotion that is being conveyed is surprise or happiness. Then the paralinguistic, as I mentioned, prosody. Like, how are you telling this? Um, let's say you are saying, "Oh wow, I really like this gift." That means your intonation is telling that, oh, you are very happy about it and you're very surprised, you were shocked that to receive the gift. Then the speaker's attributes can also be there. Like as we mentioned, that the demographics are also important. How the cultural background, the age, gender, other factors can also be there. Suppose their occupation, like this is the kind of a metadata, so this also can be used. So what is the challenges in understanding emotion through speech is like what is said. I'm feeling happy today. The content is straightforward, but however, the if the speaker pronounces with a flat tone or in a monotonous voice, then it is difficult for the listener to detect underlying emotion. Like if I just try to like why fake it like I'm happy, but then I don't sound happy, then you lack the prosody features. And how it is said, like let's say two uh, scenarios are there, then you say yes I agree, but then in the first yes I agree, and then it shows that you actually agree to it, and this is a different aspect. And then let's say second scenario, the person says, yes, I agree, but then he's not confident, he's not agreeing to you, but for the sake of argument, maybe they are just saying it, so they don't mean it. That's also, there's a hesitant tone and uncertainty associated with it. So, despite using the same words, the emotional tone differs significantly. Then who says it? Let's say teenager is there and an elderly person both say I'm not feeling any pain. Then the context varies. Like the teenager is very young, and they might also they might not feel any pain because they don't care. Like the person will get up and start playing again. But in case of elderly person, it might it might differ because there might be something wrong going on, or maybe they are having some kind of health issues. So yeah, uh, the teenager statement might be more of a positive statement. However, in case of the elderly, it might differ. It might be a negative. So yeah, these are the three factors which they can be different challenges to understand the challenges in the emotion detection. Which of the following best describes the challenge of how it is said in understanding emotion through voice? So, analyzing the speaker's accent and pronunciation, or speaker's tone and manner of speech, recognizing the linguistic origin, or identifying speaker's age and gender. So,
I think tone and manner.
yeah, exactly. Because accent and pronunciation, it depends on where you are from, like Indian accent or American accent or British accent. However, the tone and manner of speech, like we just discussed, the tone might make or break, or you can say differ, make the meaning a lot more different than what it is intended to be, right? So yeah, yeah. So it includes multiple factors like pitch variation, tempo, volume, emphasis, different words and phrases, and overall manner of speech. So it plays a crucial role. Okay, which category of voice-based data involves inducing emotions in participants through stimuli such as videos and capturing their speech responses? I briefly mentioned these data
Ma'am, you
sets.
said induced, I think.
Yeah, so
Induced.
induced is, can you guess from this uh, options? What is the most related?
Licit, elicited.
Elicited, let's see. So type of this speech data can be natural data, which is the naturally occurring speech, where the emotions are being expressed without any external stimulus. Like suppose there is an there is a cafe and two friends are talking to each other. So I you just capture the video, and there is no one, like you haven't interfered in the conversation. It's just a normal conversation going on. So that is the most natural form of emotions being expressed, because you haven't given any kind of stimulus. Let's say interviews are also there, public speech, or any kind of recording of any conversations, so where individuals express their emotions spontaneously. Then comes the simulated data. Simulated, that means to mimic, which means it is artificially, you're just mimicking something. It is acted, right? So it mimics the real life scenarios. So let's say TTS, or generating speech with emotional characteristics using actors or computer generated voices. Or you can also, yeah, actors like voice actors you mentioned. So voice actors, you can tell a person that okay, you have to speak this way, this line in maybe a happy tone, sad tone, angry tone, so they can do that for you. But that is not the most natural form of data that you will observe. Scripted data is like predefined scripts, but then scripted is like not related to emotion, but more of a you just tell what to speak, right? And then elicited means to invoke, to evoke something. It involves inducing specific emotions in participants through controlled stimuli. Now what is controlled stimuli? Let's say I play on your screen a very happy video which might induce laughter. Let's say any kind of stand-up comic performing. So it is meant to make you laugh. I know what your reaction will be, and I want to capture your genuine reaction on it. So this is induced. I'm not telling you to behave in a certain way, but then I'm giving you something which might make you behave in a certain way. So like that. Then, let me read this out. Involves inducing specific emotions in participants through controlled stimuli such as videos, images, or scenarios, and then capturing their emotional responses, including speech. So, this is slightly like not controlled, I would say, but better than the scripted or simulated. So elicited, correct. Okay, this is a, I think, factual question. So, which dataset consists of 10 German sentences spoken in different emotions by actors? And this is, let me tell you, this is the Berlin database. So, let's discuss other datasets as well. AIBO is an audio-visual recording of emotional expressions by a humanoid robot called IBO. Then, Berlin Database of Emotional Speech. This is a very popular data set. This database contains recordings of German sentences by professional actors in seven different emotional categories. Seven different categories are there. Then it like this database matches. Okay, let's see. This Ryerson audio visual database of emotional song and speech. So this dataset contains speech as well as song music also. And this is also audio visual and emotional speech is there then. So correct answer in our case is Berlin. Okay. Which of the following is not a major challenge in voice-based affect analysis? Limited availability of emotional speech synthesis, lesser accuracy than FER systems, scalability of datasets, cross dataset performance across different languages. Which is not a major challenge.
Ma'am, what are FER systems?
Facial expression recognition.
Ma'am, so I think that one too.
Yeah, correct. Because other than this option, although this is also a challenge, like not a typical challenge, but as the development goes on, we are able to make or we are able to develop better models, then accuracy can be managed, but then number one is limited availability. Now, the data sets are anything like the models are only dependent on the data sets. The good quality model will only be generated if you use a good quality data set. Then, if the data sets are very limited, then only the models generated are also revolving around the same data. Uh, then scalability of data sets. It is also a major problem because usually, like we saw in the Berlin dataset as well, seven emotion categories, but 10 sentences are being spoken, and they contain very limited number of audios. Uh, of course, it is very difficult to capture than the regular speech, so that's why maybe not many instances are there in the datasets. But what happens is deep learning algorithms are data hungry, so as if you want to make your system better, if you want to make your model better, then you should add more and more data to it because um, the more the data, better your model will learn. Typically, this happens. Then cross dataset performance. This is a major challenge that we already discussed because one dataset, let's say like we just discussed this Berlin dataset. This is German. If a model is trained on this German dataset, then it might not work well on American English dataset or Indian accent. Definitely not, because we have very different ways of expressing ourselves in every language, every dataset. Maybe Berlin one is more of a simulated, but then if you want to test your model on a naturalistic settings, it won't do well. So lesser accuracy can be handled. This is the least of our concerns. Which features are commonly used for automatic feature extraction in speech analysis? Is it the syntax and semantic, prosody and spectral, phonetics and phonology, pragmatics and discourse? So
Ma'am, prosody features.
yes, yes. Prosody. We just discussed that this is the most important, uh, like how we speak, the way of speaking of every person varies. So, in order to capture those variations, the various prosody features are there. And spectral characteristics, like we discussed in the beginning, MFCCs, and spectrograms, chromograms, like that, chromogram. So, but syntax and semantic features can be related to the grammatical structures. Like if a person is, let's say, doesn't know English and they make grammatical errors, that does not mean that the person is like has nothing to do with the emotional intelligence or emotional expression. So these features are not used. Then comes the prosody features, which are actually the correct option. Then phonetics and phonology are more related to how sounds are produced and the study of sounds within a particular language. Let's say in English, the alphabets or the sounds might be different. When Urdu and Hindi, there are multiple different sounds. In African, some tribal region, the sounds might be very, very different from what we know. So this phonetics and phonology, they tend to study that. Pragmatics and discourse, it includes the context as well. So that they're not used for this for automatic feature extraction. However, they can be like involved in the study of context and organization of language beyond the sentence level, like how it originated or what about the evolution of a language as well, like that. So we are only concerned with prosody and spectral characteristics. Okay, which library can be used to extract MFCCs from audio signals? Is it the TensorFlow, Scikit-learn, Librosa, and NumPy? I briefly mentioned this, if you remember. So TensorFlow is basically used to handle the tensors, which are basically large arrays. And what happens is that when we are dealing with deep learning, we don't deal with arrays. Array is usually like smaller in size, and the tensor is something similar to an array, you can say, but then it is optimized to be used on GPUs. So GPU, the higher like good computational resources, they tend to work on tensors rather than arrays. So arrays are usually associated with NumPy, whereas tensors are associated with TensorFlow and PyTorch. There are two libraries, there are two frameworks mainly. Then there's Scikit-learn is basically for the machine learning handling, and Librosa is the one library which is mainly used for audio analysis. Then DNumPy deals with different array-related operations. So let's read this out. TensorFlow is an open source machine learning framework developed by Google and provides this widely used for tasks like different deep learning tasks basically. Then mainly deals with the tensors, managing like tensors and all, and the whole pipeline of deep learning, deep model training, right? Then the scikit-learn is it is built on top of NumPy, SciPy, Matplotlib, so it combines and it provides efficient tools for data mining and data analysis. Now it also provides us algorithms for classification, regression, clustering. Like you can just use import the scikit-learn and sklearn dot clustering or KNN like that. You can just call it. Then Librosa is meant for audio and music analysis, and it helps us to visualize, manipulate, and extract the features. And commonly used in audio classification, music genre classification, speech recognition, and other. Then NumPy is a fundamental package which is for the scientific computing. So it is it provides support to manage the large multidimensional arrays and matrices along with other mathematical operations. So here we are dealing with Librosa, which feature is commonly used to measure the energy in an input acoustic signal. So energy, loudness, frequency, formant frequency, or speech rate. Speech rate is associated with the velocity, right? Formant frequency is related to the resonant frequencies F1 and F2 that related to some fundamental frequency. Fundamental frequency is a characteristic uh, of your voice, but does not define the energy. And so we're left with the loudness. So loudness is the perceived intensity. Like if you put more energy, then you can speak more loudly, right? So it's more of a perceived intensity or the volume of the sound. Now it is a measure of energy present in an acoustic signal, and commonly it is quantified in decibels. And fundamental frequency we've discussed is the lowest frequency of vibration of vocal cords during speech, gives us the pitch value and perceived musical pitch of a note. Now, does not directly measure the energy. Then comes the formant, which is the similar to like fundamental frequency. They just are the resonant frequencies, right? Speech rate is the velocity or the speed at which speech is produced. So loudness is the correct answer. Which attribute is commonly associated with positive voices in speech analysis? Is it the low loudness and consistent pitch, high loudness and variable pitch, low pitch and variable loudness, high pitch and consistent loudness? I want you to answer this one.
Ma'am, high pitch and consistent loudness.
So, is it associated with the positive voice?
Ma'am, like when you're excited, your pitch might be higher. That's a high pitch.
Okay, high
And
pitch
ma'am,
and
you could be, and ma'am, for loudness, it could be anything because you could not be loud and still have a positive uh,
so high pitch and
voice and
okay,
consistent loudness.
high pitch and consistent loudness. So this is like high loudness and variable pitch. Like usually negative emotions are not expressed. Um, let's say usually I'm saying it's not always the case, but then let's say you're sad or um, depressed or stressed, anxious, all the negative emotions you will put low energy, like you feel like lower on the energy side, so intensity is lower usually. Then which, as we discussed, like if I'm excited about something, I might vary my pitch, vary my the prosody will like not the prosody actually, the style or this the stress on the words will vary. Like I gave my example. I'm excited to teach, so I'm trying to make it more engaging by varying my loudness or varying my pitch. If I start speaking in a very constant tone, then it becomes very boring and it becomes less engaging. So it is an indication of uh, the excitement is missing in the tone. So usually positive emotion is a high variable, like variable pitch. Loudness we cannot like comment. Actually, I agree to some level, but then you can say that we are more loud when we are happy. So increase volume we can say. But what you were saying is high pitch and high
And consistent loudness.
consistent
Ma'am,
loudness.
because I thought that it
No.
doesn't, I mean,
Hmm.
your pitch
So
is normally higher when you're
hmm.
excited. Is that not the case?
Um, no, it's not the case. Like in in the case of anger, also pitch is high. But exceptions are always there. Like in relaxed, you might not have the high pitch. In relaxed is although a positive emotion. So it's not that straightforward, I agree. But then consistent loudness is a no for me, because loudness, when you're happy, then you are more excited. You can say that you are more on the you want to like you are more invested in the maybe statement that you're giving or talking about something. You're more it's more dear to you. Let's say you're excited and then you are talking about it. So most likely you will have some kind of fluctuations in your voice or pitch, or you want to engage the other person. So in my opinion, loudness is consistent loudness doesn't make sense to me, but high pitch might be there. But we are taking the usual case, so we can say, let's say, what is the answer? High loudness and variable. Variable pitch, I agree definitely, because more excited means you're yeah, showing variable, showing more variations in the pitch. So yeah, ambiguity, but
Ma'am, what would it be for negative voice then? Like
so
negative voices.
negative is usually associated with constant, less pitch variation. So constant pitch, or lesser, you can say actually, lesser pitch variations. And about the loudness, usually it's lower side, lower loudness. This is like what I think. Of course, emotions are not that straightforward to explain. Even nobody has, like, you cannot express what happiness exactly means to you. You can only say, I am feeling happy, but then you don't have the exact number to represent or exact definition. Like a person is smiling, then they should be happy, but no, it might be the other case. So so this whole subject, it tells us that emotions are very, subjective as well. So you cannot define it using just one definition. Uh, and these kind of ambiguities we always observe. So yeah, I mean, I cannot comment on whether this will be the best way, but in my opinion, I feel that this is the closest to what I feel, what I think this means. This is like
Yes,
negative.
ma'am, it's a bit ambiguous.
Yeah, this is ambiguous. I agree. Okay. Why speaker normalization applied? Number first option is to standardize the emotional content across different speakers to enhance the differences between angry and neutral. To accommodate variations in speech features introduced by differences in speakers' vocal qualities to eliminate differences in emotion expression caused by speaker variability.
Ma'am, C.
Yeah, correct. Because first option says that to standardize the emotional content across different speakers, that means identical normalization you are saying, but uh, we are specifically talking about speaker normalization. That means within a speaker, we are saying that we want to bring every speaker's data to the same page. Now, how do we do that? We make some internal observations and then normalize the data according to that, so that we are able to compare each and every speaker's data accordingly. So, why is it applied to enhance the differences? No, angry and neutral doesn't make sense. Like second point doesn't make sense. Third is to accommodate variations in speech features, because variations are introduced by differences in speakers' vocal qualities. My prosody might differ, my pitch might differ, my usual loudness measure might differ. So, in order to normalize that, and then I can compare with my friend's voice. Like, okay, now the loudness aspect is has been taken out of the picture. So being more loud doesn't mean being happy, or maybe I'm neutral but I'm still loud. So these differences should be eliminated. Fourth option is to eliminate differences in emotion expression. No, emotion expression is not impacted like by speaker variability. Some characteristics do vary, like we just discussed. So C option is the most appropriate here. Okay, I shouldn't mark it here. I already took an example, but let's read this out. Let's say we have two speakers, one with a naturally high-pitched voice and another with naturally low-pitched voice. If we don't normalize their speech features, the system may mistakenly associate high pitch with one emotion and low pitch with other, right? Leading to misclassifications. Let's say now we apply a speaker normalization approach, and then we can adjust for these individual differences and focus solely on the emotional cues and not the loudness, irrespective of the speaker's vocal qualities. in a way that it ensures that we don't include the system is robust and reliable across diverse speakers, and it allows us to accurately detect and classify emotions regardless of variations in the vocal characteristics. I think only one to two questions are left, so won't be much. What technique is commonly used for speech-based emotion recognition? HMMs, spectrograms, SVMs, or 1D CNN. So we already discussed this one. This is a spectrogram.
Spectrograms.
Correct. Like that. So yeah, like for emotions, angry, calm, fearful, happy, sad, different patterns might be observed. And if you see here, if you observe this carefully, so can you see the this pattern is repeating, like this is repeating here, but it is fading as we go up. This is a repetitive pattern. Same here also, like this pattern. Then it is here, then here. This is what I was talking about, the resonant frequencies. And if we go at the number, na, this will be kind of multiple of each other. Same in any spectrogram you can see. Speech is like that only. See, this pattern is repeating this zigzag. Same for this. So every emotion we can represent using some different features, and these spectrograms are also really good features. Okay, what is a major concern regarding the real-time applicability of speech-based affect recognition? Now, real-time we are talking. Lack of robust algorithms for feature extraction, variability across different individuals, computational complexity and potential exhaustion of resources, limited availability of labeled emotional datasets. Since we're talking about real-time, major concern is computational complexity because we don't want our model to take like 3 hours to give a prediction that okay the person is feeling happy. It should be as quick as possible if we're talking about real time. Other concerns are also there, but then real time, in the real time that means let's say in a let's say therapy setting where in a mental health application where you want to have smart assistants for your like smart what do we call them, therapist. So they're listening to you, the robots are listening to you, then the robot can be able to capture your facial expressions. They should know that the person is feeling low. Now I need to cheer him up. Now, if you take half an hour to just predict, then how will you react accordingly? So, what matters to us in the real time scenarios is the speed. Yeah, so we are done with this session, and I hope that you learned something out of it. And this session is like we have these sessions every Tuesday from 6 to 8. Next session will be on 4th of the March. And uh, I hope that you will join that session as well. And if you have any kind of doubts, you can please unmute and ask. I can go back to that question if you still don't did not get any point. Sahil, this was your first session, so I hope you were able to understand a bit.
Yes, ma'am. Ma'am, I actually understood a lot, even though it was my first session.
Yeah, so
Thanks so much.
it's I'm glad that you were able to catch up. So I really would suggest you to go through the. You can like I have my videos on the channel that I just shared, and you can go through the videos like maybe in 2x as well. Some it would save you some time because I have to be a bit slow in order to like make sure that everyone is able to understand. But then if you're able to do it, you can maybe 1.5x, you can cover the previous questions as well. So I think we almost cover most of the topics which are in the week's content. So if you go through the weekly sessions, I think you will be good to go for the exam. And I hope you will also be joining us in the next session. So if you are not having any doubts, let's conclude the session. So let me know.
Or and ma'am, these slides you're gonna upload somewhere.
Yeah. So there is a drive folder which is shared with all of you. I don't know how they share with you, the NPTEL team, but I have a drive folder where it is accessible to everyone. So I will
Ma'am, could you
upload this.
share that as well, if
Okay, let
possible?
me share. Just give me 1 minute. So yeah, I found the folder. Uh, can you try accessing through this link? I hope it will work.
Oh, yes, ma'am, it's accessible.
Okay, great. So you can find the previous lectures slides as well.
All right. Thank you so much,
Okay,
ma'am.
thank you for joining. I'll see you in the next sessions then.
Yes, ma'am.
Bye, everyone.
Thank you, ma'am.